So welcome everyone to day 3 of the conference. I understand we have 2 talks today, and our first speaker is Robin Deeley from Boulder, who will talk to us about a principal counterexample to the HK conjecture. So please.
Thank you for the introduction, and this is on, I think. Okay, so I'm going to talk mainly about all this stuff that's in this paper. It's already published and everything, but the archive's always the easiest place. And then if there's time, I will talk about some new stuff with Rufus Willett that's more positive, let's say, on the HK conjecture, at least the rational version of it. So also I'm going to talk about groupoids a little bit, but I'm not going to define anything. So if you don't like groupoids, you just wait for them to turn into group actions, which is where all the example will be. And so, if you don't like group actions, then you knew ahead of time at this conference what was happening, right? Okay. All right, so the conjecture. Statement, so we suppose that G is an second countable Vital, essentially principal. I'll put that in brackets. Minimal, and you think you're done, but you're not. Ample, groupoid. All right, so a number of assumptions. Then the statement is as follows. The statement is that the K-theory of the reduced groupoid C-star algebra should be isomorphic to the even odd homology of the groupoid. Okay. So that's a bit serious. Now, let's just say some things. This is what we want to compute, right? We're C-star algebraists. You've made a C-star algebra. You want to compute its K-theory. So the left-hand side is what we want to compute. The right-hand side is what we can, measured somehow, compute. So if you like the Baum-Kahn conjecture, right, this has a similar flavor to the Baum-Kahn conjecture. You have a C-star algebra you want to compute the K-theory of, and then you have an isomorphism, hopefully, that allows you to turn it into a problem that you can solve using algebraic topology. All right, so even before me and this talk, this is false. And I'm going to list some examples that were where it happened. So we have Scarparo. This is 2018. The published one, I think, is 2020. I'm using all archive dates. And then we have some others. So this is first. And then we have Scarparo. This is 2020. And then we have another one, Sanchez, and that's 2021. And the point I want to make is all of these examples are essentially principal, not principal. So I'll talk about this a little bit more, but the difference between essentially principal and principal is basically the difference between having a free action and having a topologically free action. So principal is exactly when it's actually free when we talk about these things. All right, so that's a bit heavy if you haven't seen the HK conjecture before. So I just want to get into a really concrete example, and then I'm going to talk about the counterexample, which is going to fit into a generalization of this very I would call it basic. It already showed up in Mike's talk, so we should all know and love it, I think. So it's the odometer. So we take X to be the Cantor set viewed as the set 0, 1, sequence is one-sided, and then we take a map on this. This is add 1 with carryover. And we've all seen this before, but something like this gets mapped to this. Something like this gets mapped to 0, 1. And then the only one we have to worry about is the one that's all ones and then gets mapped to all zeros. And I think we've all hopefully seen this as a nice example of an action of the integers on the Cantor set, right? This is homeomorphism, so it's generating an integer action. And we're all super happy, I think, with this. Okay, and of course, the groupoid, I'll say transformation groupoid, associated to this, let's be explicit and say it satisfies HK. So if this was the counterexample, we'd have a very, very short talk, but this is a nice example which satisfies the HK conjecture. So we're going to look at generalizing this. So generalization of this. All right, so the input is we're going to let Y be a flat manifold. So by flat, this is what I mean, and manifold, I guess I should be clear. So I want it to be closed, I want it to be connected, and flat in the sense of it being Riemann flat. So hopefully closed connected is fine. Riemann flat means that it admits at least one metric which has 0 Riemann curvature. That's the statement. That doesn't mean all the metrics have it, right? Like I have a pet peeve now that I like flat manifolds when someone shows me a donut and says it's flat, right? I mean, the torus has a flat metric, but it's not that one. Okay. All right, so the other thing we're going to have is we're going to have G mapping Y to Y and expansive. I won't define that, but I'll show you some examples. Cover, self-cover, let's say. Self-cover. Okay, so examples. Example 1, we could take Y. I'm going to just say as the unit circle, just so I can write down the map explicitly, but the map is going to be the non-trivial twofold cover of S1. And so this is a perfectly good example of a flat manifold and a map on it that you certainly see as a cover. If you draw the picture of what's happening, you sort of might get an idea of what expansiveness is, right? You take a little neighborhood and you see that in that little neighborhood, it's getting pulled apart. Right? All right, so another example. So example 2, we're going to let Y be the Klein bottle. And then we're going to have G defined, let's say, via the following picture that I'll just draw it here. All right, so there's the Klein bottle. And we want to get a cover of this, and we want it to be expansive, right? So I'm going to just draw some lines and put some Klein bottles inside of this, and we want to do it in such a way that we see this expansiveness happening. So the sort of easiest way to do this is to draw the picture like this, right? And then, you know, this square just gets expanded up to the whole square. This one is actually going to flip and then expand out, right? The other one's going to expand out. You can sort of see that this is expanding in this sort of local sense in all directions. If we wanted to have an example that wasn't expansive, right, I'll just draw one line here, and it would expand sort of in one of the directions, but not in the other. Oh, just 3 lines, get rid of these lines, right? And you would not have this expansiveness sort of happening in the Y direction. Okay, so that's the input. So back to the general case. So back to the general situation. So what are we going to do? We're going to, okay, so this whole ample talk over here means we're really looking at actions on the Cantor set. So the flat manifold is not a Cantor set, right? So we need to make a Cantor set out of this situation. So what we're going to do is, since G is an n-fold cover, like n is, you know, in this case it's 9, in that case it's 2. We have proper subgroup inclusions, where I have the fundamental group of Y, and contained inside that I have the image of the induced map on the fundamental group, and then square etc. And so now we're going to let omega I be this quotient. For people, keeping score, this doesn't have to be a normal subgroup, so I'm thinking of this just as being a set, and it's a finite set. So I'm going to be sort of careful about that. And then omega is going to be the inverse limit associated to these omega i's and coset inclusion. And then we're going to finally have, I'll put this back down in a second, gamma in fundamental group acts by the sort of obvious thing. If I have some cosets here, this equals, just put the gamma inside. And so I just multiply each one of these cosets by the gamma. Okay, and you might look at this and you say, I was promised a nice generalization of this super concrete, nice thing, and it's unclear how that's happening, right? So obviously I made up this example and chose it for a particular reason. And the reason is that this is exactly this in disguise in this case. So I'll make that an exercise since I was told we're allowed to do that. And, but I'll at least set it up a little bit. So exercise. Show that if we take y equals s1 and g twofold, non-trivial twofold cover, then we get the odometer. Maybe note to help, what do I call it, omega 1. Right, if we look at what happens in this situation, right, we're looking at this twofold cover, so we have a copy of 2z, right, and we mod out by it, we get this. And now the hint, of course, is that you shouldn't write this as 0, 1, 2, 3, right? You should write it as something in binary, 0, 0, 0, 1, 1, 0, 1, 1, and sort of think, how is this map going to go? And you make this inverse limit, right? It's going to. Sorry? Omega. So omega in general is just a Cantor set. In this particular case, because they're normal subgroups, right? Then yeah, so I mean, if it's not, if this isn't, yeah. Even if they're not normal, I think, I guess it is a group in subset. Yeah, I guess the completion is a group. Yeah, that's true. But each one of these is not a group. Like that's yeah. Okay, and then dot. Right? You keep doing this, and you recognize what it is. All right. Okay, so that's the situation. So this is a nice collection of examples. So let's maybe do a little groupoid versus group action chart. So we have group action. Groupoid. All right, so we want our groupoid to be second countable. So we want our group to be countable, and we want X. X is going to be a Cantor set in the end, but let's say it's second countable for now. Then we look over there and we say, what was next? I don't even know what's next on the list, but it's how it appears to be. Tau, so we want the G to be discrete. We want this to be essentially principal, but let's just say principal because that's what we're going for. So we want the action to be free. Or let's just say free. We want the groupoid to be minimal. So we hope that that's what minimal means for the action, but and it is. And finally, we want it to be ample, so we want X to be X. And this is ample. Right, so this is for all the people, or I don't know, maybe everyone like me has now embraced groupoids, but if you haven't, this is the point. You can just think of the conjecture in this way for group actions. So looking at free and minimal group actions of discrete groups on the Cantor set. That's the context. All right. All right, so now to make a counterexample, what we of course need to do is be able to compute the thing that I said we usually can't compute, and then compute the other side as well. So for this class of examples, we have that. So basically, let's say, Poirot proved the following. So theorem, let's just say it like this. So the homology of the groupoid associated to this, so I'm going to write the groupoid associated to this as omega, and then with pi 1. And this is isomorphic to a stationary inductive limit with the homology. And here, maybe I'll just emphasize this is the same map each time. Let's say that's 1. And then 2, if we look at the K-theory of the reduced C-star algebra of this groupoid, which is just the cross product, this is isomorphic to the K-homology of Y. And again, it's stationary. It's an inductive limit, excuse me. It's not just that group. It's an inductive limit. And again, this is the same map each time. So we're looking at this. This is, changing the problem of computing the K-theory and the homology of this groupoid into classic algebraic topology in some sense, right? You need to compute the homology of this space. You need to compute the K-homology of this space. I should say furthermore, maybe a remark. This isn't so important in the talk, but the relevant maps in these inductive limits is the transfer map. So again, because this is just an aside, if you know what the transfer map is, you know this is something in algebraic topology, so it's completely an algebraic topology problem, computing the K-theory, or the K-theory of this C-star algebra and computing the homology of this groupoid. So it's completely reduced to something you could, give to your favorite algebraic topology friend and say, help me out computing this. Okay, so that's a remark. So now based on this, we want what, right? Well, if we're trying to make a counterexample, we're trying to be in a situation where these things don't match up. And so step 1 would be we want to make these not match up. Right? And then hope that in the inductive limit, we can, sort of maintain the failure of these two things to be the same. Again, like this is going to be graded even and odd when we're doing it. Okay, so we want to find a flat manifold Y with homology not isomorphic to, let's write it like this, direct sum over I, and then, so that's, just to be clear, that's not an immediate proof that it's a counterexample, right? But that's the starting point to trying to get one, right? Having this failure happening at the space level already. Oh, so this is z coefficients. All of it's z coefficients. Yeah. You can see the torsion exactly. Sorry. You can see the yeah, yeah. Yeah. So yeah, that's true. So when we get to this stuff with Rufus, we'll move to like rational or even complex coefficients, and then we'll be killing the torsion. And then the conjecture is going to be, with some Baum-Kahn assumptions, going to be okay in this transformation groupoid case. Yeah. All right. Okay, so we have all this. Oh, I should mention, maybe I was remiss to not mention that, over here, this expansiveness assumption is exactly the assumption that's getting us freeness of this action. So, there is something going on with this assumption. So most of the other things are fine, right? We're already on the Cantor set. We're already going to be a discrete group because we're the fundamental group. The minimalness of this odometer action, that's a classic thing, but it's the expansiveness that's getting us the freeness of this action. Okay. All right, so here's the proposition. So there exists a flat. Oh, maybe, sorry, I could do it this way, but let's do it this way. So for each d greater than or equal to 9, there exists a flat manifold Y with two things happening. One is the dimension is equal to d, and two, the following holds. So the torsion in the K homology of Y, which is a finite group. So T of G, this denotes the torsion subgroup. So this is a finite group, so I'm taking the number of elements in this. This is strictly less than the number of elements in the torsion subgroup of the homology. Now, did I put a T? No, I did. I don't want. Right, so it's slightly stronger than saying just the groups are not isomorphic. We've actually got that they have different numbers of elements. And so just, I'm not going to do the proof or anything, but the key ideas in the proof, or I don't know if it's ideas, or just some things you can, if you know, you'll recognize, let's say. So the first one, maybe it's a little bit, maybe everyone is not that up on their flat manifolds. I certainly wasn't, 3 years ago. When was this happening? 2 years ago? I did not know much about flat manifolds, I have to admit. But so flat manifolds are a really interesting class, but they're also super well understood, right? So for every dimension, there's a finite number of these flat manifolds. For example, in dimension 3, there's 10 of them. We probably can guess in dimension 1, it's the circle. In dimension 2, it's the Klein bottle and the torus, and then sort of goes on like this. So there's a subclass called real Bott manifolds. So this particular manifold is a real bot manifold. So this is mainly, if you're interested in this counterexample, then you can Google real bot manifolds, look up what this class of flat manifolds is and how they're sort of built. And how it's used is we just have more information about things like the cohomology ring of this class of flat manifolds and things like this. All right, and then 2, this one's the one that maybe everyone knows is coming. So there's the Atiyah-Hutzenbrook spectral sequence, which allows one to relate exactly these two things, the k-homology or the k-theory. The k-theory would be related to the cohomology. The k-homology is related to the homology. And basically, all we're looking for is some example where the Atiyah-Hutzenbrook spectral sequence, some of the torsion gets killed by the differentials. Right? And so that's why this 9 or greater sort of shows up. We have to go to a dimension high enough so that these are non-trivial and we're actually killing some of the torsion. Okay. So let me put this back up. All right, so the next theorem we're going to use, now we have a theorem. So far, right, we've got maybe even a little bit more than we essentially on the nose need. We've got something a little bit more controlled than just these are not isomorphic. We have a statement about the number of elements. So the next theorem is due to Epstein and Schub. They did not state it like this, but I'm going to state it like this, and it's their results, right? If you look at their paper, what they do leads to exactly what I'm about to say. So for each flat manifold, Y, there exists a expansive self-cover G such that the following holds. So we're going to look at the torsion sitting inside of the homology of our groupoid. And that's going to be isomorphic to the torsion. Oh, actually, maybe we don't have to go grade it like this. This is a little bit more complicated. So just look at the homology of the two objects in mind, right? So the first one is the homology of the groupoid. The second one's the homology of Y. And what this amounts to, if we go back to R missing from here. This result right here, what is this saying? It's saying that the connecting maps in here are an isomorphism on the torsion subgroup, right? So they're preserving the torsion subgroup all the way along. So in a shocking event, I already erased it, but in the example of that Klein model, right, the Klein model has some torsion in its homology. So you take this exact 9-fold cover, and you notice that when you do this covering map, it's actually an isomorphism on that part of it. So that's the one you want to sort of take in that case, and more generally that it has that kind of flavor of expanding in all the directions that you have. All right, so now I think we're ready for counterexample time. We have this, yep. All right, so now the counterexample. All right, so we take Y and G as in the last two results. So we're taking Y like this in this proposition, and then we're using Epstein-Shub to pick a particular self-cover that has this property. So then, what do we have? Well, we're looking at the torsion sitting inside the K-homology, or the K-theory, excuse me, of the reduced C-star algebra of omega and our pi y. Right, so the number of elements in that is going to be less than or equal to the number of elements in the torsion subgroup of the space Y. It's cohomology. So this is the thing that maybe takes a moment to recognize, but we're looking at a stationary inductive limit. So the way you prove this is, you know that this is a finite group, and you just say, suppose we had more elements, right? What do? In this inductive limit, you push them all to one group, right? Because you can push them along, and then the pigeonhole principle, right, is going to say at least two of them are the same. So you can't be making more elements. Of course, if it wasn't stationary, all bets are off, right? The groups can make the torsion get bigger and things like this, right? But that takes a moment. Then we've got that this is strictly less. That's what we have up there. Then the direct sum of H plus 2I and this. And then we have that this actually equals on the nose the homology. Oh, I did not put a T. Apologies. This is the torsion subgroup of this graded H star plus 2I omega. Maybe I should just move this down. Oh, I have to tell everyone. Everyone's okay with me writing like what's happening at each line by line, right? And then at the very end we go, this is leading to a strict inequality, right? It clarifies things for me when I'm going line by line, whether we're doing an equals or whether we're actually doing an inequality of some kind. Okay. So this is plus 2I omega. All right, so we put it all together and we have our counterexample, right? Because the torsion subgroups of these two abelian groups we're interested in now are definitely different, so they can't be the same just as groups, right? We even have something a little bit stronger because we have that the number of elements is strictly less. Okay. All right, let's fix this one. All right, so maybe some obvious things someone might say is like why, I sort of explained why 9 in the context of this proposition, but it doesn't seem entirely necessary for the whole construction. So this is true. So a PhD student of mine, Rachel Chaser. So this is maybe a remark. So Chaser. This is, let's say, in progress, but it's done and getting written up. Proves, let's say, constructs a flat manifold of dimension 4 that leads, and let's say leads to counterexample to the HK-conjecture. So by leads, I mean, like we've done this construction, right? There's this generalized odometer that's associated to any flat manifold, and you've picked a particular self-cover, and then you do this process. Of course, importantly here, this dimension being 4, we know that we can't get a result as strong as this, right? The torsion subgroups are actually going to have the same number of elements. So the work was really showing that those torsion subgroups are different and that that's preserved in these inductive limits. So if you, like for non-flat manifolds, the classic example is RP4, right? RP4 is an example of a manifold where the K-theory and the cohomology are different, but it's not flat, so you have to work quite a bit harder, right, to make this, find this flat manifold. It's sort of interesting because you say construct sometimes, right, but there's a list of all the four-dimensional flat manifolds, so one in principle could be like, I'm gonna just go down this list and hope for the best. She didn't do that, but that's a possibility. All right, so maybe we'll make this remarks. This is the first one. The second one, this is maybe to give all of you a hint as to how I came to this, right? Because maybe people who know me know that I like Smale spaces, so I have to maybe mention them in most of my talks. So I'm going to mention Smale spaces just briefly. So associated to Y and G is a Smale space this is X equaling this inverse limit of YG. So this is these Wheeler solenoids, Williams solenoids, these kind of things that Mike mentioned in his talk. And this, there's a Morita equivalence of these groupoids. So omega, this one right here is groupoid equivalent to the unstable groupoid. Of, I'll just call it X, phi. Phi is, of course, this shift back map in this inductive limit. Like you just apply G to all the elements. Again, this is not going to come up too much in the talk, right? This is the only time I'm really going to mention it. But I just wanted to sort of say that there's this relationship between this odometer action and these Smale spaces. Yep. So the flat manifold isn't a big deal. This Epstein-Shub result is actually the existence of the Mon-flat manifolds. So it's a big question whether there are these expansive self-covers, whether they exist on some manifolds. And there's pretty serious obstructions to them existing. I can't remember all the terms, but it's quite a restricted class. And flat manifolds are sort of the, maybe I'd say the biggest class where you just know that you always have one, right? So that's how that's coming in. Yeah, I mean, for the odometer, this generalization of these odometers, this is, you know, there are much more general odometers, right? There's no reason why we have to be taking the fundamental group and quotienting all the same, right? We could just, you know, make a Cantor set out of some chains of groups and, you know, have a group act on it, right? So, you know, this is just a mild generalization. Yeah, so just to continue on this lines for one more second. So as soon as you see the unstable groupoid show up and you have a way of computing its K-theory as this inductive limit, you might ask what's happening for the stable algebra. And so the stable algebra, you get the same sort of thing. So the last thing I'll say about Smale spaces is, moreover, if S is the stable algebra, let's say of X or phi, then what would we hope the K-theory of this algebra is? Well, it turns out to be a stationary inductive limit. Now, with the K-theory of Y. So there's this sort of duality sort of going on between sort of the K-homology and the K-theory and the stable and the unstable algebras in this type of situation. let's say, the next unnatural question. All right, so we have these counterexamples to this conjecture, right? Even like, so first of all, there was the essentially principal counterexample. So what do you do with the conjecture? You delete essentially, and you keep principal, right? Now you have these counterexamples that are principal showing up. So what do you do to the conjecture, especially in light of how these counterexamples are showing up with this torsion, right? You rationalize both sides, tensor with the rational numbers, and now you ask the conjecture again. So does the HK-conjecture hold rationally? So i.e., is there, well, let's just write it down. So we do K theory of the reduced groupoid C-star algebra, tensor with Q to make it a vector space, and then we do the same thing over here. Right, so first of all, clearly, what we were talking about before with the torsion, right, is all of a sudden going to get killed by this tensoring with the rational numbers process. So it's sort of removing that issue. However, so maybe remark 1 is Puro example is, let's say, already a counterexample. So in the essentially principal case, this is already false, right? The example already given, the very first one works at the level of the rank, right? Seeing the rank of this. I should say this is not my conjecture or Rufus's conjecture or anything, right? This was in Matui's original paper on the HK conjecture, right? So there was the HK conjecture and there was the rational HK conjecture, like back to back, right? They were both conjecture. So it's already a counterexample. 2, for the examples, let's say 4. The examples. Oh, maybe I should also say, I think it's really important that Matui, stood up and said, this is a conjecture, and we all got to do a bunch of work based on it, right? Like that's an important thing. Like even though it's false, it's really good that this conjecture was made, that it holds in a bunch of cases, and that I get to write a paper that has a counterexample, right? This is a good deal for me. All right, for the examples constructed from flat manifolds, the rational version holds. Just to maybe talk about this very briefly, right? The idea, so we want to use 2 facts. So one is that the transfer map is a rational isomorphism. That's 1, and 2, the Chern character is a rational isomorphism 2. Right, so I erased it now, but we still have something similar up there with the stable algebra, right? So we have a Chern character that's going to map from, say, the K theory or the K homology of the flat manifold to the homology of the flat manifold. That rationally is going to be an isomorphism, but we still have to worry about the inductive limits. But the map in the inductive limit is this transfer map, which is a rational isomorphism. So we have, everything working the way we want it to. Okay. All right. Plan was to have 10 minutes, but we have 5, so that'll be fine. All right. right, so here's the theorem with Rufus that's in progress, or also done but not written up. So we're going to suppose that we have x being acted on, let's just say G acting on X as above. So G discrete, G countable, discrete, X cantor, let's say, etc. Right, so free action, right, etc. All these things. Let's make it discrete. Okay. Let's assume, let's say, if G is torsion free and the Bohm-Kahn conjecture with coefficients in C of X holds, then the rational HK-conjecture holds. Right, so maybe to give context, this, of course, implies 2 right off the bat before you do any work. That's a special case. And so let's just say key parts of the proof. So basically, the first thing is, what does Bohm-Kahn give you? Well, Bohm-Kahn gives you a statement like this. So we have G, we have C of E of G. We could use E bar of G, but it's torsion free, so they're the same. It's all good. We have C of X, and we know that by Bohm-Kahn that this is isomorphic to the K homology, or the K theory again. Sorry, of this, and we've got X on G. Right, so we have already a reduction of trying to compute the K theory of this C-star algebra into something more topological, some K homology type group, and then 2, Jeff Raven has a Chern character. Let's say has defined Chern character, which let's say after some work maps from the left-hand side to groupoid homology. So Jeff did not define his Chern character immediately to write this groupoid homology with some other theory that he was working with, and the real work, right, was actually showing that that lines up with, I mean, it's not crazy, it's what's expected, let's say, but in general, this sort of points to a general, this should always sort of work when you have a Bohm-Kahn assumption, right? The thing that you have to do after you make this Bohm-Kahn assumption is have some sort of explicit Chern character type map that's mapping to the groupoid homology, and that's sort of one way to approach this conjecture in a fair amount of generality. I should say that I'm only talking about the torsion-free case. There is a way to refine this for when you actually are dealing with an essentially principal groupoid. All of a sudden you find out that the left-hand side of Bohm-Kahn is picking up more information than what you would expect from the conjecture, and then the Chern character that you're defining doesn't map to groupoid homology. It maps to something a little bit more sophisticated, but not much. Right? So that's how that goes. All right, so I'm out of time, so thank you for your attention.